reminder of what we've been doing so far. I know it's been a while since Monday, but we've been talking about how to find the derivatives of certain types of functions, right? For example, didn't mean to do that. We had the product rule when we had things being multiplied, right? That's when we applied the product rule. When we saw division, like two functions being divided by each other, we had the quotient rule. Then we got into this problem here, and it was the derivative of x plus 2 cubed. Now, this is technically a product, and you actually can use either the product rule or if you FOIL it once, or just the power rule if you FOIL it out the whole way to find the derivative of this guy. But what we did is we introduced this thing called a substitution, right? And instead of writing the inside function, we just wrote u. Okay, so we just let u be the inside function. Okay, we knew the derivative of u, which we call du dx. We knew the derivative of y, which was dy d. Oh, sorry, this was dy du. Okay, and if we strung them together like a chain, we got that dy dx was the derivative of y with respect to u times the derivative of u with respect to x. Okay, so essentially what we did is we kind of multiplied two derivatives together, and then we kind of stuck the inside function back in. This is an example of the chain rule. Okay, and this is a rule that you're eventually going to be able to do in your head. By the end of class, we're not going to have to write the substitution and find the derivatives of each of them and string them together. It's actually kind of an easier concept because what we had was an inside function, which was x plus 2. And we had an outside function, which was something being cubed, right? We had an outside function, something to the third power. Okay. Essentially, if you don't see it yet, we'll go through another example. But I took the derivative of the outside function, which became here, right? And I multiplied it by the derivative of the inside function. Okay. Now I know this seems kind of weird right now, so if you have questions, hold it off until we do the next example, where we kind of do this a little bit more streamlined. But before we get into that example, let me just tell you the formal definition of the chain rule. Okay, so I wouldn't really worry about all of this up top. It's kind of just conditions for the chain rule, which I'll always kind of give you. Okay, but it's telling us that we have this function, big F of x. Okay, and this function says we have an inside function g, and we have an outside function f. Okay, so I know this doesn't look like what I wrote on the last page, but it's telling me that the derivative of this composition is the outside's derivative. So this is the derivative of the outside evaluated at the inside function, and we'll see how that plays out in an example later. And we're going to multiply it by the derivative of the inside. Derivative of the inside. Okay, now this is a different notation, which we use to kind of introduce it. I don't like either of these notations when I do the chain rule. I don't think it's very illuminating to me, especially when I'm trying to do it really fast. So the way I like to think of it is the derivative using the chain rule is going to be the derivative of the outside function, leaving the inside alone, times the derivative of the inside function. That's the way I like to think of the chain rule. Okay. Now, if that made any sense to you, congratulations. Let's do an actual example, and I think it will make things a little bit easier. Yeah. Yeah. Yeah, I'll post this. I'd say for now, let's hold off on questions about the abstract. Let's do an actual example and see how this plays out. Okay. So here's an example of something to the 100th power. Okay, now what I could do is I could multiply this out 100 times, and I promise you we won't do that ever in this class. We could do that, and that would be fine. But I think the chain rule is a good idea because we have an inside and an outside, okay? Any ideas on what the inside function is? I think I heard it all around, right? X cubed minus 1, right? That looks like it's on the inside because we have parentheses around it, right? Okay. And what I'm going to say the outside function is, it's going to be something raised to 100, right? I pretty much wrote everything except that 100th power. I'm going to make a little box to the, not the third power, to the 100th power. Okay, so the box is kind of like my X variable, okay? Box to the 100th power. Okay. When we find the derivative of this using the chain rule, I need to find the derivative of the outside function first, okay? What is the derivative of my outside function?
100 to the 99th power.
Good, 100 blank to the 999 power. No, 99 power, good. Okay, so I literally just took the derivative of my outside function, okay? So that is the first part. Then the next part is to find the derivative of the inside. What's the derivative of x cubed minus 1?
3x to the second power.
3x to the square. The derivative of minus 1 is just 0, so I'm just going to leave that alone. Okay, we're almost done, but I need to leave the inside alone. What is my box? Like, what represents that box in my outside function? X cubed minus 1, that's the inside. Okay, so in total, my derivative is, I guess I can multiply the 3 and the 100 to get 300, right? I have x squared and x cubed minus 1 to the 99th power. Okay. Does that kind of make more sense with the example? Okay, so essentially what we're doing is we're choosing our outside function. We're choosing our inside function. We're going to find the outside function, leaving kind of like a blank, essentially. You don't have to do this, but it's easier for me to think of it that way. And then we find the derivative of the outside and multiply it by the derivative of the inside. Okay. How confident do you feel in doing example 15? All right, I think we're good. I'm going to give you a few minutes to give this one a try. You can talk amongst yourselves if you want to, and then we'll come back in a little bit. All right, I think everyone is on the right track here. I'm going to go through this step by step just because I think in the beginning we need to see this a little bit slower. So same sort of deal, right? We have an inside function. We have an outside function. Okay, what did you guys say your inside function was? Perfect, x to the 14th plus 17. That's the thing that's on the inside. And the outside function is everything else, right? We have our inside function being raised to the 12th power. Okay, so that's kind of what we're dealing with here. Okay, I guess I need to find the derivative of the outside. And what is that derivative? Right, write it down. Not 11. 12. Box to the 11th, good. Okay. Now, if you don't feel like writing the box and you can kind of do this in your head a little bit quicker, that's fine. But for now, we'll do this. Okay. And I need to multiply this by the derivative of the inside. What's my derivative of the inside? What's the derivative of the inside? 14x to the 13th. Good. Okay. Now at this point, all I have to do is write my inside function in the box, right? X to the 14th plus 17. Okay. So in total, and I'm not very good at arithmetic, but I think 14 times 12 is 168 because I wrote that down. We have x to the 13th and we got x to the 14th plus 17, all raised to the 11th power. Okay. Any questions on example 15? All right. Oh, okay. All right. So let's go to the next question. Okay. Now, the inside and outside doesn't just have to be a polynomial. We can do different types of functions and the chain rule at the same time. For example, we have e to the 2x to the 7th plus 14x, okay? Now, still, we might have an inside and outside function, so let's write that down. We don't have something taken to a power anymore. We have e to something. What do you think the inside function is this time?
1.
Not 1.
2x to the 7th power plus 14x.
Yeah, 2x to the 7th power plus 14x, right? So the inside here is, well, what's being applied to e? Okay, e is kind of the outside function, okay? So I guess e would be our function e to the power is our outside function. So the inside is kind of the power of our function this time, okay? All right, let's do chain rule. What's the derivative of the outside function? What's the derivative of e to the something? In the box, good. So that's the derivative of the outside. What's the derivative of the inside?
14x to the 6th power plus 14.
Great, 14x to the 6th power plus 14. Now, we're done, but we definitely shouldn't leave a box there because that's not a function. Let's put our inside function in the box. And to clean things up, we know that our function e to the 2x to the 7th plus 14x times 14x to the 6th plus 14 is our derivative. Okay. Any questions before we go on? Okay. Let me do one more and I'll try to leave you on your own, okay? Going to example 16, we have 1 over something, okay? Now, I know this might be a little bit tricky. The way I like to do stuff whenever I see a fraction is to change the fraction into something that has a negative exponent. And the reason because of this is it just makes it a little bit easier for me to understand using the power rule since we have that rule. So what's another way to write 1 over 3x plus 2 as 3x plus 2 to a power? Not -1, but -2, good. Okay, so negative exponents mean fractions, okay? Let's take a look at the inside here. What do you think the inside of this one is? 3x plus 2, good. Yeah. It's still early. And what's the outside function? Blank to the -2, good. Okay, now I know a lot of stuff that you'll see will use like u instead of a blank. I like the blank because I can literally just fill in the blank, okay? I don't know why, it just makes it easier for me to see. Okay, so derivative of the outside. Well, what is the derivative of the outside?
1, not to -2.
Mhm.
-3.
Blank to the -3, good. Okay, so that's the derivative of the outside function. And the derivative of the inside function is derivative of 3x plus 2. 3, good. Okay, now we're not done yet. We have to fill in our blank. Okay, put that in parentheses, by the way. And we are left with -6 times 3x plus 2 to the -3. Okay. Now, of course, when we simplify things, negative exponents aren't really simplified. What's another way to write this in terms of fractions? Perfect. -6 or 3x plus 2 to the 3rd power. Okay. I'm going to give you some time to work on example number 17. And I'm going to give you time to work on 18 as well. I was seeing some nice work as I've been walking around. Let's go down to example number 17. Okay. So this one I think was a little bit tricky. Now, let's kind of just go through this real quick. Who did I get to write this one up? Was it Blake? Now Blake used a U instead of a box, but U is totally fine as well. Do you kind of want to take us through your steps here?
Yeah, so I set that u equals 16x squared plus 3x plus 1.
Mm-hmm,
And then I just rewrote the function as u to the 1/4.
mm-hmm,
And the derivative of that is 1/4 u to the negative 3/4. Then you multiply that by the derivative of u, so it'd be 32x plus 3.
mm-hmm.
And then you just plug in u for the 16x squared plus 3x plus 1 for u. And then we simplify, you get 32x plus 3 over 4th roots of 16x squared plus 3x plus 1 cubed.
Nice job. So one thing great job on this, Blake. One thing I want to say in this question, Blake, instead of using u, instead of using the box, he used a u. That's totally fine. But if you're a little confused, that is where we got that. Does anyone want to see how the negative 3/4 turn into a 4th root at the end? Let me just go through that real quick, okay? So let me just show an extra step from here to here, okay? I know that a negative exponent just means put it on the bottom, right? So this becomes 32x plus 3 on top. 1/4 means that 4 is on the bottom. Oh. And I can change the negative 3/4 to a positive 3/4 as long as it's on the bottom, okay? Now to go from this step to this one, we know that a 4th root means 4 in the denominator, okay? So the reason Blake put a 4 here was because there's a 4 in the denominator in the exponent, and he just kept the 3 as the numerator, okay? Any questions on example 17? I know it was a little bit tricky, but I think we're good. Let's go to example 18, okay? This one was kind of similar, but instead of having a square root or something, we have a negative root instead. Maddie, do you kind of want to take us through your steps here?
So I first made it not a fraction, so I made it negative 7.
Mhm.
And then I did the derivative of the outside. So the function, the derivative, and the derivative inside 27 plus 2. And then I
Mhm.
the square root of the bottom. So I forgot the
Oh yeah, you forgot the the 8 there, but yeah. Mhm. Any questions on example number 18? All right. Okay, so let's go to example number 19. I've got, I guess this is our last one, right? Okay, so we have y equals e to the x. Okay, so we don't have to have polynomials as our inside function. We can also have other functions. Let's take a look at what we do here. Okay. What do you think my inside function is? E to the x, right? And not just e to the x, any of them. It's specifically this one, right? It's the e to the x up top in the exponent, okay? So the inside function is e to the x. What's my outside function? E to the something, right? So if I put these equations together, I would just stick my inside function in the box and it looked like the question, right? Okay, so what's the derivative of my outside function? E to the something, right? Okay. What's the derivative of the inside function? E to the x, good. So plugging in my box, I have e to the x, okay? And piecing everything together, we have e to the x times e to the x. I know it looks a little funky, but yes, we can have functions that look like this as well. Any questions on example 19? All right. Wow, I greatly underestimated the time it would take to do this class. So I guess I'll let you go. I don't have anything else to tell you. So we'll do more practice on this. If you need, my suggestion is to do more practice questions on the chain rule. I put a lot on my classes. So make sure you're practicing and I will see you tomorrow.